So, yesterday we started talking about the comparison between surface and groundwater. We talked about the quantity issue. Oh, so now that is AC. No, it's working. It's working. The quality issue. Now coming down to sustainability. Which one do you think is more sustainable? By sustainability, how does it, which one is more sustainable over long period of time? The groundwater? How so?
For example, if you have your groundwater source, I mean you have a borehole and you're tapping from it, you must have done your pumping test and all that to make sure that it doesn't.
And how does it compare with the sustainability of surface water?
Seasonally?
Pumping test is usually to what? The yield of the aquifer. So how does that affect sustainability?
In the case of surface water, it goes with season. There are some seasons where you have less water to have, depending on.
But you have some rivers, streams that are perennial. Yeah, of course, it is a fact that there is seasonal variation in the flow for surface water. During the rainy season, it is highest, of course, because you have a lot of input from precipitation. While during dry season, you experience low flows in some instances, even no flow at all in some instances. Yeah, so that is how we are comparing the two. So, what do you want to say about groundwater? How does it affect groundwater? In what way?
To reference to the ideological cycle, they say there is part of the water that percolates down to the groundwater table.
Yeah.
I'm talking about the seasonal variation. When there is, let's say, the dry season now, when the fall is low, this same water added to the groundwater table will be minimal. That talk about the reduction in the 100.
That is relative. It's relative if we go. Oh, I think we will. Okay, there is a slide in the next. Let me quickly. Okay, that is relative. Relative in the sense that it depends on the aquifer from which you are abstracting the water. If it's unconfined aquifer, which is when you reach the water table, it usually gives you the Freeatic surface of the unconfined aquifer. So if your source of water, be it well, borehole, or whatever, is just penetrating only the unconfined aquifer, then that seasonal variation will have great impact because the water table fluctuates with season. When it receives a lot of input from precipitation during the rainy season, it goes up. During dry season, it goes down due to abstraction activities. But the unconfined aquifer, the deeper layers, the deeper aquifers, let's assume you are receiving your water from this aquifer. Okay? Then, as we are going to see later, you usually have an outcrop, a point where it receives recharge. Because if you remember, a confined aquifer is just like a conduit. The water in the confined aquifer is under pressure, is pressurized. Meaning, when you have, let's say, a conduit flowing, under pressure, you now, let's say, put a piezometer, it will flow up, isn't it? So the same thing here, let's say your well or whatever is up to this. And then Okay, yeah. So let's say it is up to this. So you can see for this aquifer, this is the recharge area. The source of water for this aquifer is from this area, not really from the overlying aquifer, because it is assumed that this is an aquitard. An aquitard is an impervious stratum. It doesn't allow the passage of water through it, although it may allow, but minimally. So it is assumed to be impervious. And for our modeling purposes, when we are deriving the boundary conditions, these are called no-flow boundaries. Okay, but that we will discuss when we start the modeling proper. Okay, so this one is receiving its water from this recharge area. Okay, so of course, it depends on the source, precipitation and what have you will now determine. Okay, but by and large, the extent of the impact will not be as great as that of the unconfined aquifer, the rate at which the water reduces. We are going to see later, today probably, we'll talk about what is called the compressibility of water, total stress, effective stress, and the fluid stress. And why is it that, let's say, when you have an unconfined aquifer, you will keep on pumping, but effectively the volume of water will not be generally affected. We are going to discuss that probably today, okay? But by and large, yes, so that is why, like from the beginning I said, it's relative, isn't it? It is relative. You may not say precisely sometimes that surface water, yeah, groundwater may be more sustainable probably, but that depends on the aquifer you are tapping from. Is it the unconfined? Unconfined is usually not stable. It fluctuates over time. But for the confined aquifer, then that one is more stable and more sustainable. And in that case, relatively, you may say that the groundwater in some instances could be more sustainable than surface water in some instances. Okay? But, you know, it is not something like a clear-cut answer. Okay? Now, going back to sustainability contamination. Quick, fast. Because we have just taken our breakfast, so we should vibrate at the highest frequency.
Surface water
Contamination.
more prone to contamination than the groundwater.
Surface is more prone, okay.
And also, in the zone where the groundwater is prone to contamination due to filtration and other means, due to the quantity of that contaminant that will get to be, the magnitude of the contaminant.
What will reduce the quantity?
I'm talking about the area where the groundwater itself is even prone to contaminants. Due to the self-filtration, the subprovide layer, it will have reduced the magnitude of the contaminant itself. Only in the case of the one that has to do with the rock, all these contaminants in the rock.
Yeah, as you mentioned, by and large, surface water is more prone to contamination because it is open. From wind, from anthropogenic activities, and all that. Okay? So you have a lot of contamination for the surface water, and for that, it requires higher amount of treatment because it is usually more contaminated. But the groundwater usually is less contaminated. Although that one could also be relative in the sense that if the groundwater is in an area that is, you have a lot of industrial activities in which there is no proper disposal method of the waste, hazardous waste and what have you, then the groundwater of the area will also be contaminated. Just go to the Niger Delta. You dig a well or whatever, you'll just be smelling petrol, kerosene and what have you. So the groundwater is terribly contaminated. And that's why they have like one of the highest pollution cases, because recently, I think as far back as 2012 or so, the United Nations Environmental Protection and what have you analyzed the cost that it will take to clean up the Niger Delta area as a result of the contamination by due to oil exploration. And they came out with about $1 billion is required to clean up the area. And that was the highest or the greatest clean-up process that has ever happened in the world. Currently, they have started, the clean-up process. The former Minister of Environment, before she left, she launched the program and what have you. So I don't know the state now, but I know they have started the process of the remediation of the area as a result of oil exploration. So in such area, then probably even the surface water is contaminated. So in that area, you can say both. None is carrying any additional weight than the other, probably. Okay? But by and large, generally speaking, groundwater is less contaminated by and large. But even that one has to be careful when saying that, because sometimes it is site specific. Let's say you have a house, you have soak away pit here, there, and you sink a well. Be careful. You have done that in hydrology, all the considerations that need to be done, the distance between well and any source of contamination, and whether it will be upstream or downstream and all that, okay? And about the casing and the finishing of the well, okay? But by and large, groundwater is usually cleaner than surface water and requires less amount of treatment. As I mentioned, more often than not, depending on the borehole or well, you may just need filtration and some disinfection, because over time, of course, microbes try to grow, so some amount of disinfection is also needed. But if your well is well cased and what have you, so probably the amount of debris will reduce as you pump the water out of the well. Okay? Yes? In what? Of? Okay.
So even they are not well, their water is leaky. Some of their bottles are also leaky water. Is it part of the contamination?
Kaolin is what? What is kaolin? What? No, I know. It's a type of soil, isn't it? So for that, what about filtration? Can filtration do away with the kaolin? Because it's just like, let's say, clay, but very fine one. Am I right? So what else can you do with that? Because by and large, soil in particular, as we are going to see, may not be a source of contamination per se, but it depends, because usually soil has associated heavy metals. Most of the soil you see, when you test for heavy metals, you will find. And some of the heavy metals may be in excessive limits, beyond the maximum allowable contaminant level. So that will be the main concern. The kaolin, is it pure kaolin, or what are the contaminants around it? You don't find soil to be pure in its pristine state. No. You have associated heavy metals attached with soil at all points and at any point in time. So that will be the concern. What are the contaminants? And then the way to now do away with that. And then another thing, as we are going to see, probably because the kaolin may be at a particular layer, I will go to that. Probably if you dig further, but that will mean, more cost. Because normally you may have just hand-dug wells. Hand-dug wells maybe 6 meters, 5 meters, 9 meters. Even the borehole here maybe 30 meters and what have you. But when carefully studied and explored, that challenge could be overcome. But the geological formation and the aquifer depth has to be well studied. Now, exploration. Which one is easier to explore? I think we discussed this before, isn't it? About the exploration. For the surface water, you need dam. That's the first thing. You need dam, and building dam is really not an easy task. And then you need the intake structure, the conveyance structure, and then the treatment plant, and then the distribution network, and then the storage tanks, and then whole lot of investment is needed. For the groundwater, it also depends, in the sense that you can only remove the dam as the source of water and use groundwater to pump to the treatment plant. So now it will reduce the cost as well. The cost is going to be reduced because the cost of sinking, let's say, borehole will not be compared to that of installing or constructing a dam, obviously. But then for domestic, individual house supplies, you can just dig your well, your borehole, and then you have your water. Okay? So for the exploration, by and large, the groundwater is simpler and easier to explore than surface water. Because surface water, because of the inherent contamination, you don't usually find it suitable to be used immediately. It needs to be treated. So this is like the water table, and then because of this depression, it contributes. So here you have a flowing river, okay, which now links, you have a link between the surface water and the groundwater, and the groundwater now sustains the flow in streams, okay? In some instances it may not be this way, okay? These are another relative merits of surface and subsurface reservoirs. Surface reservoirs, subsurface reservoirs, which is for the groundwater. Here you have few new sites that are free for the surface reservoir. This is for US. Many large capacity sites are available for the groundwater. And high evaporative loss. This is another disadvantage, because if you will do the water balance for a reservoir, you will realize that it has a high evaporative loss. Okay? Huge amount of water is lost daily as a result of evaporation. So it has high evaporation loss, even where humid climate prevails. Because when you have humid climate, so there's already a lot of moisture in the atmosphere, which will in a way slow down the evaporation. In this case, practically no evaporative loss. It is already covered. Okay, even if, let's say, it evaporates, it becomes moisture. Okay, within the soil moisture. Need large areas of land, obviously, for construction of dams and what have you. Need very small areas of land just to sink your borehole, and that's it. May fail catastrophically when you have a dam and you have dam break. That is a catastrophic event, okay? And practically no danger of failure. Of course, we know sometimes borehole can fail, but by caving in, but nothing will happen to the structure, or, or anything of that sort. And it has varying water temperature because of the direct contact with the sunlight, and this one, water temperature is usually uniform, because it's usually deeper down. Easily polluted, usually high biological purity, although pollution can occur. This we discussed extensively. Easily contaminated by radioactive fallout, not rapidly contaminated by radioactive fallout. And water must be conveyed. That is one thing. And in this case, act as conveyance systems, thus obviating the need for pipes and canals. You just pump it up and that's it. But all this, you see, some of these are relative depending on the particular system of interest you are considering. Okay? Now, I've started discussing about this. This is, you have a pumped well pumping from the unconfined aquifer. This is the water table. Over time, days, years, will expect some sag, okay? Some kind of depression as a result of the abstraction that is taking place. Over days, it may be this level. Over years, it may be that level. And that is why more often than not, during the dry season, starting from January, usually February, through April, May, before the rain becomes stable, you realize most of the wells now will be dried up. Or sometimes you will have to wait until there is recovery. You wait overnight. When they recover, you now pump it out like that. But this happens because, one, when we were growing up, hardly do you find a well. Our well, I mean, inside our house, it doesn't dry up at all. But later, over time, you have population explosion, urbanization, and what have you, a lot of other wells, a lot of boreholes around, which are usually abstracting from the same aquifer, the same unconfined aquifer. Because if you have a well here and your borehole is into this aquifer, then they are not connected practically, isn't it? But if you have a well here and then a borehole, then you know that that borehole will affect the surrounding wells around it, okay? And that will now affect the water level over time, okay? We are going to discuss, because you see this is the confining bed, which is an aquitard, and then this is another aquifer, and this is another one. Here it is assumed that when you have a lot of abstractions, the water level will reduce, will affect this, but that is really simplified. We will expatiate more as we move on. So now we discuss about the water hydrologic cycle and some few aspects about the groundwater. Now we'll take the main matrix of where the groundwater is found, the medium, which is the porous media, okay? As we mentioned in the outline, for the porous media, here we'll discuss what is it made of, and then we'll discuss about the aquifer, and then the types of aquifer. That is as far as this slide is concerned. And then in the next one, we'll discuss about the aquifer properties. The aquifer properties. If you look at all that we are saying right from the beginning, probably there is nothing new. But like I said, we cannot assume that all the, I mean, you all have this. Yeah, of course you did them before, but it has to be reviewed thoroughly. Because now you are considering the groundwater system and you are trying to model it. So all these aspects, at one point or the other, you will find them useful during the modeling process. Okay, so you need to understand the hydrology. You need to understand the processes taking place in the groundwater, in the porous media, little about the unsaturated area, more about the saturated zone. Okay? Now, porous media consists of soils and rocks. Just the soil we have, the matrix, okay? Soils and rocks, and porous media hold water, air, and contaminants, which can be dissolved solids, chemical pollutants, dissolved. The chemical pollutants can be dissolved heavy metals, which are dissolved in the water, or are attached to the soil matrix, which is the porous media. They can be attached to the porous media. And heavy metals, as we also know, most of them have low solubility in water. Most of them, except few that they have varying solubilities in water. So, depending on that, that is what will determine how they dissolve in water. Okay? But more often than not, like I mentioned, when you have a soil matrix, you will realize that it has heavy metals, and that is obviously because of the fact that you have a lot of underlying rocks. Most of these soils are formed from rock minerals, which are made up of different metals. Okay, so you can have dissolved heavy metals and hydrocarbons, which are usually, for the hydrocarbons you have polar and non-polar. I hope your chemistry is still sound. What is polar and non-polar? Can you tell me? Yeah, and non-polar. You see, in the modeling, we will go back to the SS1 chemistry down to wherever you are now. Okay? What is polar and non-polar? But when I mentioned it, you didn't raise up your hand to ask what is that. And I told you that you have to understand everything as clear as possible. If there is anything that is not clear to you, you have to make sure that you understand it. Not just assume, okay, I will find out all this or that. If not, when I pose a question to you and you couldn't answer it, then you'll be in trouble. Yes?
It's like you want to charge positive
I don't understand. I didn't get your answer.
Like the polar is the one that charge has a positive charging.
What is it? What you mean the hydrocarbon?
No, the polar
Is one that has charge,
positive charge.
and the non-polar,
Fraction.
and the non-polar has negative?
Yes.
Huh?
That's right.
Negative? Yes.
Generally, hydrocarbons are compounds made from hydrogen and carbon. So non-polar are all those hydrocarbons that consist only hydrogen and carbon. But sometimes hydrogen group like chlorine, fluorine, iodine, bromine.
So they are non-polar. If you have
Combine.
other compounds.
Combining these hydrocarbons to make it polar. You want to
So non-polar are the ones with other compounds, apart from hydrogen and carbon, right? No. No. Who will tell me what is polar and non-polar compound? And you have to tell me. I will not tell you.
Polar
Yes.
has a combination of a cation and an anion. For example, water has the positive hydrogen ion and the negative hydrogen. So a polar compound is that which can be come in contact with water, which is a polar.
Which what? Which?
Polar compound. When they come in contact with water, the positive will attach with the positive and negative with the negative. Non-polar are those that have only positive or only negative.
So what is their relationship with water?
Water is polar.
No. You said the polar, when they come in contact with water, what happens?
They will dissolve because polar and polar are coming together.
Okay, so non-polar, what will happen if you have a non-polar compound? What
Just
is?
the positive?
No, what is its relationship with water?
It cannot dissolve.
Polar can
immediately.
any compound that can dissolve in water are polar. Well, those that cannot dissolve in water, except from petrol or paraffin and whatever, are not polar. Because the polar compounds.
So can you have a hydrocarbon that is non-polar, that is polar?
No.
No. Why no?
Because hydrocarbons formed by coordinate covalent bonding.
Yes.
Something like that.
Yes, go ahead. And what does that imply? Go ahead. What does that imply? What about
It implies that
what about alcohol, ethanol? You know ethanol, alcohol. Is it miscible with water? It is, right?
yes.
Is it a hydrocarbon?
Yes, it's hydrocarbon.
Okay, so what happened in that case? All right. So some of you have idea what polar and non-polar compounds are. Yes, of course, polar compounds, whether hydrocarbon or non-hydrocarbon, are those that are miscible with water. Okay? That are miscible with water. And non-polar are those that are not miscible with water. Then if you go deeper, probably you can discuss about the bond and what have you that makes it miscible. But of course, for hydrocarbon, you have polar and non-polar. Polar are those that are miscible with water. Example, you have phenol, you have alcohol, ethanol. All those are miscible with water. Okay? And probably you can talk about the functional group. The particular functional group, depending on what the functional group is, it will be either miscible or not miscible. You have like ethanoic acid, because it has the OH, isn't it? When you dissolve something in water, you know, it will now dissociate. It dissociates because of the functional group. You have the hydroxyl group. Okay? You know the dissociation of compound in water. For the non-polar, it does not dissociate at all. Let's say you have ethane, methane, and what have you. It has no functional group like OH, in which, you know, when you put in water, because water is already dissociated into the hydroxyl or hydroxonium and the hydroxyl group. Sorry, the hydroxide. Okay, so each one will now surround and then pull it apart and then dissolve it inside. But one that do not have the functional group, like the non-polar group, then they will not dissolve. But one thing is that for hydrocarbon you have polar and non-polar. Okay. Then you have the bacteria, viruses, and what have you. All these are also principal components of soil. If you take any soil, it has some bacteria, some viruses, and what have you. And how do you determine that? By what is called the organic carbon. Although the organic carbon, it tells you a lot about a lot of other things, okay? But most soil also has some pathogens, okay? Now, what are the different zones of porous media? The first one, you have the vadose zone, which is also called the unsaturated zone, and contains soil moisture. This is the water table. Above it, you have the unsaturated zone, or the zone of aeration, or the vadose zone, or the suspended water, or whatever you call it. Okay? It contains the soil moisture. Okay? And Richard's equation is often used to mathematically model the movement of water in the unsaturated zone. You know Richard's equation, right? You must have done this probably in the groundwater hydrology. I don't know if you have done it in soil engineering, soil science. Okay? So we use Richard's equation to model the movement of water in the unsaturated zone. And here you have the soil water, and then we have the intermediate vadose water, and we have the fringe water. The fringe water is the water at the capillary fringe. We are going to discuss what the capillary fringe is. It's like an intermediary between the unsaturated zone and the saturated zone. So it is not fully saturated, yet its moisture content, the amount of water it has, it is almost saturated. It is almost saturated, and it overlies the water table. It overlies the water table. And this is the belt of soil water, this is the intermediate belt, and this is the capillary fringe. Capillary fringe, because the water in the unsaturated zone is held by capillary forces. We all know what capillary forces are, isn't it? From our physics 131 and what have you. Okay? They are held by capillary forces because it is not saturated. So the soil moisture is held onto the porous media or the soil matrix by capillary forces. And these capillary forces are what? What makes up the capillary forces? What? What are they? These are general cohesive force and adhesive. What are they in particular? In specific? What pressure? Water pressure? Hydrostatic pressure?
Pressure against atmospheric pressure. The water pressure against atmospheric pressure.
Atmospheric pressure? The first thing you do in fluid mechanics is what? Brain 201. Properties of water, right? Surface tension. I told you we'll go down to as far as SS1 and then come up to the level wherever you are. The first thing you do in fluid mechanics is properties of water, where you discuss capillarity, you discuss surface tension. Surface tension forces. You have the surface tension forces and you have the interfacial tension forces. Because we have seen that in the unsaturated zone, you don't have only one phase. You have water, you have air. And in some instances, you can have contaminants. Either oil, aqueous or non-aqueous, isn't it? You have the surface tension. When you have water inside anything, it caves. isn't it? Downward. This is concave. Upward or downward? Yeah, what do you call this? Concave upward or downward?
Downward.
Hmm?
Downward, concave.
Concave downward. All of you? Huh? And you all failed. And you all failed. This is concave upward. It is the other one. When you have, let's say, mercury, this is concave downward. What?
Convex.
I didn't say convex. I say concave upward or downward. I didn't say concave or convex. This is concave upward, this is concave downward. And water behaves this way as a result of the surface tension, because at the interface there's unequal attraction here. You know, water has what is called hydrogen bond, isn't it? So inside here you have H ions and OH ions in form of hydroxonium ion. Okay, so they are pulling the molecules on the surface because there are more of them inside. Because water is a polar compound, so that's why you have this tension. So the force is unbalanced. Here you have the atmospheric pressure acting. Okay, that is surface tension, and that's what is making it to stick. That is why it weights. If you remember your SS1 physics, one of the advantages, that's why it weights containers, it weights, things, because of the surface tension. And that's why mercury does not weight, because it doesn't have the surface tension, it's just not there. Do you understand? The surface tension is what is making it now stick to the grains, to the porous media, to form moisture. The surface tension and the interfacial forces, interfacial tension forces. Okay? These are the two that form the capillary forces. We will discuss this more when we start to discuss about the contaminant transport. Because in the contaminant transport, all this will have a role to play in the movement of the contaminant as it moves from the unsaturated zone to the saturated zone. Okay? Okay, I didn't finish with this. Okay. So this is the Vedas zone. Then the capillary fringe, which is the fringe water, like I mentioned. Now, what about the pressure? What will you say about the pressure in the unsaturated zone?
In the unsaturated.
Yes. What will you say about the pressure in the unsaturated zone?
It's just the atmospheric pressure.
What?
It is just the atmospheric pressure.
So it's equal to the atmospheric pressure?
Yes.
Am I right to say that? Abdullah.
Because I know definitely it is atmospheric pressure here.
You are the experts here, isn't it? You are the experts. Because these are all, if you see, all these are just like preliminary. Am I right? But like I said,
Currently we can say
you must get them right before we start drafting any complex equation here and there. You must get all these things right ab initio. They're equal.
There's something like because
The same fluid mechanics. Rain 201. Let's go down. Let's still go down to rain 201. Let's still go down to rain 201. Then move to soil science, engineering soil science. 1 and 2. Probably I think should be 2. Rain 304. You have dealt with the unsaturated zone, because in that case it was describing, things taking place from physics point of view in the unsaturated zone. Isn't it? So the pressure is atmospheric, right? And you all failed. Oh. I'm counting your number of failures. I'm counting your number of failures. Today you had 2 consensuses on failure. Suction. Can you remember something called suction? Suction head in the soil science? Oh. Suction head. Huh? None of you? Or is it that all of you finished from other schools? I can say most of you finished from here. Am I right? So you must have passed engineering soil science. You can't remember anything called suction head? Suction? So what about it? What is it about that? Suction is what? Is it positive pressure or negative?
It's negative.
It's negative. Is that what is prevalent in the unsaturated or on the surface or where?
Unsaturated.
So now you can remember, right? That the pressure in the unsaturated zone is negative. It is not positive. And it is not atmospheric. Okay? It is not positive and it is not atmospheric. It is negative. That's why it is called suction. Suction, because you'll feel as if, you are sucking the air. Later, we are going to discuss more about the different types of pressure. We'll still go back to RAIN 201. We'll still go back to RAIN 201. Because in this case, you really have to understand, because later on we are going down to something called pressure head. So you need to really understand what is that pressure head and what are the different types of pressure that you have. And you know all this. You did them in RAIN 201. RAIN 201. So maybe you may need to go and review. I may not mention just one course, because in this you can see we are touching RAIN 201, engineering soil science, fluid mechanics, hydrology and hydraulics, and then we go everywhere. But what it means is that those basics, they have to be always clear with you. Okay? Now, the capillary fringe, I made mention of the capillary fringe, that it is intermediary between the unsaturated zone and the saturated zone. It is not fully saturated, yet its moisture content is higher than the unsaturated zone. Okay? So, much as we mentioned also that the pressure in the unsaturated is negative. Later we are going to, what is negative pressure? Do you even have it? What is the real implication of negative pressure? How do you visualize it? We are going to discuss that. Just like I mentioned that we will discuss about all the different types of pressures that we have. Okay? So the water pressure is less than atmospheric, which is negative, under suction or tension. You must have had this word, tension or suction, in engineering soil science. And that's what it's referring to. Suction head, tension head. In fact, what do you use to determine the tensiometer, isn't it? Can you remember that? You are not as old as I am, so at least I took this course years ahead of you. So your brain should think faster than mine, isn't it? So the pressure is negative in the capillary fringe. Like I said, we are going to examine that and discuss exactly what do we mean by that. What are the pressures? Why is it negative? Okay? And it is almost saturated. You can see it is almost saturated. Water is held by surface tension and capillary forces, which are the interfacial forces. Water is not available to wells, although it is almost saturated, but water is not available to wells. By available to wells, it means the water doesn't flow under gravity, isn't it? It does not flow under gravity. Later, when discussing all the different properties of the aquifer, of the porous media, we will talk about the different parameters, which you are also aware. But now, all these parameters, you see, when we come to modeling, all these parameters, the aquifer properties, we didn't talk about porosity yet. We'll talk about it, specific yield and what have you. They will all be like an input into our governing equation. And for anything to be an input into your governing equation, you have to understand it very well. How does it vary? What does it depend on? How does it behave? So that is why we need to go down from ground zero, as if you don't know anything on groundwater. If you look at the level at which we are moving, it's as if, I'm assuming as if you don't know anything on groundwater at all. Like this is your first class on groundwater, isn't it? But that is how it should be. Because we move from zero to hero. Gradually we'll be moving up. And then we'll come up to the level that you are. But we cannot just start from the middle and then move up. No. We have to go down and then gradually build up and then we move up. It is not available to wells and it may vary from 2.5 cm for fine gravel to 200 centimeter for silt. Why does it vary? We are going to see that when you have clay, the porosity increases and the moisture also increases. The retention, the specific retention in silt, fine silt clay, the retention, the specific retention is higher for fine grained soil than for coarse soil. And the specific retention is telling you about the amount of water it can hold against gravity. Against gravity. All these terms probably before, you just memorize, okay, specific retention is the amount of, because probably you are thinking in the exams, the instructor can just ask you, define this, define that. No, in this case, it goes beyond definition or memorization. But you really need to understand every parameter and be able to appreciate it. Not just memorize the definition. No, memorization here doesn't work at all. But you need to understand it the way it is. Okay? We'll discuss that, like I mentioned, under the aquifer properties. Okay? Because the way it is, we'll take the aquifer properties and then we review some hydraulics of the confined and unconfined aquifer, and then we move down gradually. Because we will have, okay, this is the first lecture. No, this is the second lecture, but I call it lecture 1. After the lecture 2, we will have to go back to your vectors, your vector algebra, and dust it off. That is Math 106. I don't know if it is called with that name up till now. The same thing you did, your vector algebra, Math 106, we'll go back there. The same thing you studied, and it will be, probably before then, it will be good for you before we take, because after lecture 1, we'll take lecture 2, then we'll go and review the vector algebra before we take the next lecture. So probably I will suggest that you go back home, get your Math 106 notebook, and go over it. If you crash it that time, if you just memorize just to pass and get the grade, this time it will not work. In the sense that it is not about memorizing, but you really have to understand it very well. So we'll go back and review the vector algebra, the vector, the arithmetic, and what have you. And then we move on. Because in modeling, terms are usually, more often than not, they are expressed in vectors. So you must understand the vector algebra very well. No two ways about it. Because as we are going to see more often than not, you have most of the parameters not being one-dimensional. There are 2, 3-dimensional, which is even the real situation. But depending on the model, sometimes you can make it one-dimensional, 2, or if you want to reproduce the system as it is, then you have to go for the 3D model, which is much more difficult because the more the number of dimensions, the more is the difficulty. And all this will now be more or less expressed in vector forms. Okay, so we'll have to go back and review our vector algebra. And that's why, like I was saying, the modeling process is not really difficult per se, but it has a lot of other things that will make it solid. So all this will have to be done, and then we move on. This is just 1 hour, so at least I still have 1 more hour. Let me give you just break for 5 minutes. Now, back to business. Our break time is over. Yes, our break time is over. So, Just above the water table, moisture content decreases with height. Okay. Above the water table, the moisture content decreases with height up to the ground surface, where you have the, let's say this is the water table, and this is the ground surface. Okay, so the moisture content decreases with height. It is highest at the capillary fringe, no, at the water table, because that is saturated 100% moisture content. The capillary fringe has not 100% moisture content, but less than that, but almost saturated. It is almost saturated because, and it is just because of the fact that the water in the capillary fringe is held by capillary forces. So it may practically be saturated, but yet you can't take it out because the water is held by capillary forces. Okay? But then in the water table, it is available. And then the moisture content reduces up to the surface of up to the ground surface. Okay? This, like I said, the dynamics of the unsaturated zone, we'll study it, we'll come back to it later when we will look at the contaminant transport aspect. Okay? We'll look at it in greater detail, but we are just like introducing now. We have the Freeatic surface, which is the water table surface. Okay? Here, for the Freeatic surface, what is the pressure? Now, let's go back to pressure. We just finished brainstorming. You can see we are moving gradually from the unsaturated capillary fringe down to the saturated zone. Okay? So what is the pressure? Is atmospheric? It's equal to. So the pressure is atmospheric. So meaning much the same way as it is atmospheric for surface water in the sea, it is also atmospheric on the surface of the groundwater, isn't it? Okay. So yes, granted and accepted in this case, though I didn't ask whether all of you have agreed or not, so that I can now have the number of failures versus the number of success. Okay. So here the pressure is atmospheric. Okay. The pore water pressure equals atmospheric pressure at the surface of the water table, isn't it? This is the surface, right? What about when you go inside? Now, what is the pressure? Like I mentioned, one thing with modeling, you really need to understand the system as best as possible. This is not a class for you, let's say, to memorize, okay, this and no. You have passed that stage. This is, you have to understand it very well. You have to understand, all these are basics, of course. There is nothing advanced here, am I right? Nothing. But probably the depth at which we are going, or the understanding, yeah, you might have had it then, but then it didn't matter because probably the implication was not there, you know. But now is the time when all the understanding has to be with you before we start the actual modeling. So now, back to my question. What is the pressure inside the water? Like some point here. Yes. My friend over there. What about you? Can you help him out? Bail him out. Can you bail him out? Is Abdul Qadir aware? Tanimu. After the class, just let him know because he wanted to attend the other.
Where is it? Side down or surface?
Look at this is the surface, right? Okay, water table, right? This is the surface. So inside, let's point X. Let me call this point X. So is it clear now? What about you? I think I will have to force it on you to go back and review all your hydraulics, all your hydrology, and then so that you will be up to date. Yes? It is still atmospheric pressure.
The pressure is above
Then we probably will go back to physics in SS1.
It's
Yeah.
above atmospheric pressure.
It is above?
Yes.
Is it above atmospheric?
It's just before water pressure.
Eh?
It's just before water pressure.
So it is atmospheric.
No, it is not.
The pore water pressure we said. So what do you mean by it is just the pore water pressure? How do you relate it with atmospheric? Is it above, below, equal?
No, it is above.
Above. Why is it above? If I agree with that. Yes, granted. It is above atmospheric pressure. But why is it above atmospheric pressure?
As you say, it's a combination of the atmospheric pressure and the water head that we have there.
And the water head. Good. If you haven't answered this question, I will have asked you to go and get. Then we were using PN or KK. I don't know whether it is still available now. I would have asked you to go and review PN or KK, review the pressure topic. Okay? Yes. What is pressure, by the way? No. Oh, that's why you can also my area. So you all know what is the definition, isn't it? But the real, okay, don't worry, we'll go deeper down into. Pressure is the force acting normally on the area, isn't it? Okay? That is what is defined as pressure. Why are we saying atmospheric pressure? The atmosphere is filled with air, isn't it? Although the amount of air as you move up, is it constant? Up. This is the ground surface, right? As you move up, is the amount of air, is it constant in the atmosphere? I mean, with respect to height, when I move up, it varies. Does it increase or decrease? It increases. It increases.
It decreases.
Hmm? Then we will have to vote. We will have to vote. It seems there could be equal on each side. I mean, there could be equal number. So, those increases. Let me see your hands up so that I can count.
In the subsurface or on the surface?
No, from the ground surface, when you move up, the altitude, does it increase or decrease? So that's what I'm saying. So does it? Those are after increase. Increase. Only 3. But you must vote because there will be. I mean, when voting, there are those that can abstain from voting, right? In this case, no. So 3. Those saying it decreases. Okay, some are having. Okay, I have 3, 4, and against 1, 2, 5, 6, 7, 7, 3, 10. So I have 5 that will have to tell me their own view. Yeah. Those that have not voted at all, let me see your hands up first. There are, I think, about 5. All of you here? You there? And you, right? Okay, 5. Okay, so let me start with you. So tell me. You neither vote for or against. So what is your state? It remains stable? No. It remains constant? Okay, then let me go for constant, which is the third option. It remains constant. The amount of air remains constant, irrespective of the height. Let me see your hands. Then what is your own opinion?
I go with increase.
What?
I go with increase.
With increase, so 3 plus 1. Oh, okay, let's vote again. It looks like you have different views now. Increase now. Increase 1, 2, 3, 4, 5, 6. Oh, it has doubled now. Decrease 1, 2, 3, 4, 5. Oh, constant. Neither increase nor decrease. Constant. Nobody? So I have 6 against 5. You have not voted up till now. You are afraid of voting or what?
No.
You all did geography.
I don't think.
You all did geography. Am I right?
I don't think it's a matter of voting.
Yeah, but I am assessing your input and the side that you belong to.
Yes, what I'm saying.
So it's a matter of voting.
What I'm saying is,
If all of you, if you have a consensus, then we can move ahead and then see. But there is no consensus here.
okay, what I'm saying is that it is you know, when you look at from the ionosphere, the troposphere, and all this, you find out that what happened is that as you move, the variation in the movement of molecules varies, and
so there is neither increase nor decrease. It depends.
As such,
is that?
As such.
No, is that what you're after?
No, it increases.
Okay, it increases.
Yes.
So you are after increase, right?
Yes.
So let's reserve your comment for now. So increase 7. What about you? Increase 8. You also increase, right? Yeah, you have already voted. What about you? Increase or decrease? Okay.
It is seasonal variation.
Okay.
Air and wind is seasonal variation.
Okay. So it varies. It can increase or decrease. No particular pattern, right? Depending on certain variables, right? Okay. Who else? Who else has not voted? Who else has not voted? Now, let's go back to, is it cosmology or geography? Geography, I suppose. You have air surrounding us, isn't it? You have planets, isn't it? Right? You have the sun, and then you have, what other planet after sun? Oh, Jupiter. All these are very, very important. You may think they are nothing, but I tell you, they are very, very important, because we are talking about atmospheric pressure here, right? Isn't it? We need to understand exactly what is that atmospheric pressure and how does it vary, because it affects our system variables. So we really need to not just memorize, okay, atmospheric pressure is equal to 101.3 kilopascal, or it's equal to 1 atmosphere, or it's equal to 76 millimeter of mercury, or it's equal to 10 meter of water. No, you have to go beyond that. You need to really understand exactly what it is. We have air surrounding us. We have different planets, isn't it? Right? Here on Earth we have seasonal variation, isn't it? Rainy season, this season. What about in other planets? Do you have seasons? Now you will say, I'm taking you to geography. Yes, I'm taking you to geography, because it is affecting our system, groundwater. You all did geography, right?
Yes, the basic geography we did, they didn't talk about the seasonal variation and other planets. We were only taught the number of planets we have.
You did the properties. You must have done the properties of each planet. Huh. In the solar system, you have the planet, and then you will know. Even my kids in the primary school now, I think they will be, okay, Jupiter, this is closer to the sun, this is hottest, this is this is that. Oh, and now you're telling me that.
Sir, I can categorically say the geography we did
maybe
far different from the one they are doing now. Talking about the primary school nowadays, the way they are being taught is different from the way
okay, now we have atmosphere. Is it all the planets that has atmosphere? Let's go to that now.
Well, majorly we concentrate on Earth.
Is it all the planets that has atmosphere? You have no idea about that.
Not all.
Not all.
Not all.
So some have.
Not all has.
Some have. Okay. Now let's come down to our point of our topic of discussion. The atmosphere, the air surrounding us. It is exerting pressure, isn't it? When I place this, it has weight. It exerts pressure around the area, okay? And the pressure is force over area. The air surrounding us is exerting pressure on all objects on the earth, isn't it? So that is what is called the atmospheric pressure. Pressure due to the atmosphere. An atmosphere is consisting of air, isn't it? Do you have vacuum in the atmosphere? I mean, in the space. When I say space, I mean the cosmos. You know the cosmos? The cosmos. The galaxies, stars, when you go billions and billions of kilometers away from the Earth. Okay, now, what happens to when you are boiling water? What happens when you move to a higher altitude? Does water boil faster or slower? Like here on Earth? Okay, now, let's say on ground level, I want to boil water. Let's say it takes me 5 minutes. When I move, let's say, 1 kilometer up, let's say there is a mountain. Let's say Mount Everest, which is about 10 kilometers above the sea level, isn't it? I think it's the tallest, right? About 10 kilometers above the sea level. So, do you think it will take me the same 5 minutes to boil water? Why?
Because the air is more than the air. It's down.
The higher the altitude, the lower the temperature.
Oh, you are taking us to something else which is also wrong. The higher the altitude, the what? The lower the... The higher the altitude, the lower the temperature. Okay. But do you know that when you are flying in aeroplane, you know, you are surviving on air conditioning, isn't it? The air has to be cooled. The air, it has to be heated up.
Are you talking about the air inside the plane or the outside?
No, the air outside. Okay, let's keep that. When you move up, you said it boils faster because what?
I did not say that.
No, someone is saying because the higher you go, the cooler it is, isn't it?
Yes.
Yes, I agree. The higher you go, the cooler it becomes. Yes, granted. But how does that increase the rate at which it boils? What? Which pressure? You have forgot all your basics. This is physics SS1, SS2. Vapor pressure, isn't it? Vapor pressure, right? And vapor pressure is affected by what? By the atmospheric pressure, isn't it? When you move up, the pressure, the atmospheric pressure reduces. So all those that have said increases, no. It reduces up to a point where you don't even have atmosphere. Because deep down in space, you have absolute vacuum. Although you have energy moving in and out. So it may not be absolute vacuum. But one thing that is for certain is that as you move up, the atmosphere reduces. Up to a point where you don't even have air. And that's why at such an altitude, let's say 10 kilometers, because that is the height at which most of the aeroplanes fly. About 10 kilometers up, above sea level. At such an altitude, the amount of air there is not the same amount as you have. It's extremely less. So the air has to be compressed before they supply it to you. And that's why should you, let's say, come out, you'll suffocate. Because you won't have oxygen to breathe. Did you get my point? You won't have oxygen to breathe. Because the amount of air is so small at that altitude. So the air has to be compressed. And when it is compressed, it gets hot. Then they have to cool the air again before they now supply it to you. You, the guys waiting, or in the aeroplane. Because once you compress, then heat is generated. You did thermodynamics, isn't it? So what I'm saying is that the atmosphere reduces when you move up. And probably this is the only planet that we have atmosphere. Because the atmosphere is what is also responsible for the seasonal variations that we have. Our Creator specially designed it to be suitable for humans, for the inhabitation of life. Okay? So the same atmosphere, when you come down, up to the sea level, the ground surface, that is where it is highest. Do you understand? But it is not constant as you move up. It reduces. And that is why when you boil water at higher altitudes, it boils at lower temperatures. Because the saturated vapor pressure has to be equal to the atmospheric pressure. That's the condition for boiling. The saturated vapor pressure has to be equal to the atmospheric pressure before it boils. On the water, on the ground surface, the sea level, the atmospheric pressure is 101 kilopascal. At about 10 kilometers, it may be, let's say 30. Let's assume. So that means the saturated water vapor pressure will easily be equal to this at shorter time than this, isn't it? So it will boil faster. Do you understand? Okay? And also boiling can occur when you have negative pressure. You will see bubbles coming out when you have negative pressure. How do you examine that? When you have water in syringe and you pull it up, you can see bubbles because it is under suction. Are you getting it? Now our explanation of atmospheric pressure has taken us to thermodynamics, to geography and what have you. But this is very important that we have to know, okay? That the atmospheric pressure is more or less constant on the surface of the earth, but as you move up, it reduces up to a point where it is zero. Okay? Up to a point where it is zero. Because the atmospheric pressure is also like due to the earth's gravity. It is the earth's gravity that is holding the atmosphere. The earth's gravity. Okay? But let's not go so much into that. But let's understand that the atmospheric pressure reduces when you move up. Okay? And then now, coming back to our point, you remember I just asked you this question, right? And that is what now took us into this. But even if I will spend 1 hour on this, I will do that until you get the correct information. Now, the pressure here is atmospheric. When you go down, you have column of water, isn't it? That will create additional pressure in addition to the atmospheric pressure. Okay? So the pressure will depend at the point and will be given by the atmospheric pressure plus the pressure due to the height of the water column above it. Okay? So it is not constant, but it is certainly more than the atmospheric pressure. Is that clear? But when you move up, it is negative because it is under suction, under tension. Okay? It is under tension. All right. I was only trying to explain this, the pore water pressure equal atmospheric pressure. And then normally coincides with the water table. The Freeatic surface, it normally coincides with the water table. Why do we say normally? It means not all the time. I told you that the capillary fringe is what? Almost saturated. Isn't it? But I told you that the pressure in the capillary fringe is not atmospheric. It's under suction. It is negative. So it may appear that this is the water table, while really that is the surface of the capillary fringe, not the water table. Is that clear? Yes. So that's why normally coincides with the water table. So it is not like at all times. Okay? The slope gives the direction of groundwater movement in an unconfined aquifer. The slope of the water table, it gives the direction of the general, the shape, it gives the direction. although later we will talk about the direction of groundwater, let's assume we have, this is the ground surface, okay? Another question, so get ready. Oh no, like this. Which one will be the correct slope of the water table? Let's say in this case, this is the ground surface coming down. Is it this one or that one?
I understand this. The top one is what?
This is the ground surface. So these are two different slopes for the ground, for the water table. Do you understand? So I'm asking, which one will be the correct slope of the water table?
The green.
We have to vote again. Okay. Black. Let me start with the black. Hands up. Black. 1, 2, 3, 4, 5. 5. Okay. Black, 5. Green. 1, 2, 3, 4. Only 4? Then it means 4.
Green 4.
Oh, sorry. So the other about 6. What is your own opinion? Is it flat? Is it zigzag? Or what?
Nature of how before we got.
So you said slope of the water table.
Yes. I mean just the shape, the top.
Top.
Yeah, the water table shape.
Why do you have to?
Go ahead.
Why do you have to be like that? I mean,
What is your own opinion? Tell me.
I don't even understand why it's going to be
Okay, you see, this is the shape of the ground surface going down. So do we expect it to the water also, the water table, to follow the ground undulation, the ground surface pattern, or go against it? Did you get my point? Yeah. So that is what I'm just.
The last statement has said.
Sorry, I want to take my
The last statement says the slope of the groundwater
determines the direction.
determines.
Yeah. In this case, this is the slope, so the direction is definitely this way. In this case, it is definitely that way. No. Wait. In this case, it is that way. In this case, yeah. So now, talk. That's why it is early in the morning. So you must have taken your breakfast. You are full of energy, and so your brain.
So let's vote again.
Huh? What?
He changed his mind.
He changed his mind. Okay, so +1 minus 1. Oh no. +1 minus 1. Okay. Green also.
Yes.
Oh, green is gathering momentum. Black +1. Green +1. Green +1. Who else? Green. Oh, green is. Yes. So now here we have 5, and on this side 5, 6, 7, 8, 9. Oh. Still someone has not voted. Did you vote?
No.
So what is?
I have questions to ask.
Go ahead.
From the last statement on the board, we said that the slope of the slope gives the direction of the groundwater. So then, in this regard, that is that of the aquifer. In this regard, we have what is this line representing?
The water table, the top of the Freeatic surface, the water table. The top of the water table, the surface. Yeah. So meaning if it is like this, then the direction of the groundwater is also towards that.
So now, we have 2 arrows.
Yeah.
This.
Yes.
So, where is the direction of the groundwater?
Well, I have indicated for this one, for the black one, this way, For the green one, that way.
So that means there's no need to talk about which one is it, where is the water.
No, I'm not talking. I'm not asking about the direction, but which one will be like the correct water table shape. Simple. I'm not talking about the direction in particular.
Okay.
Yes.
The shape of the water table.
Yes, like which one will it be?
Okay. Now that's good. What you say.
So what is now in your stand?
No, you said which one will be the direction of the water?
Whichever way, because the direction is already indicated. So is the water table going to be this way or that way?
Is the black?
Sir, this the shape is how the water table should be.
So why is it black? Why is it green? Now,
Black.
let's discuss. No, let's talk. Why is it black? Why is it green? Blue. Is it green or blue?
The
Green.
reason why I chose green is that there is this statement that says that the water table is normally lower.
Which one did you choose?
I chose green.
Green. Okay.
Yes. Let's say there is this statement that says water table at the valley is lower at the margin, or let's say plateau is high. So the water will be accumulated, will be flowing towards the high side, looking at the cover of the ground. Now that was the direction of choosing green.
And then anybody for choosing black? You have to talk. I will not be the only one talking. And you have all those that five have chosen black. So you must tell me something. Yes.
I choose black because the water table has to follow the same topography.
The topography of the surface, which is exactly the catch I use in getting you. It can be this, it can be that. It can be this, it can be that.
But sir,
Why I ask this question is to test, to see whether you feel that the water table has to follow the topography of the ground surface. Sometimes it does, and sometimes it doesn't.
sir,
So there is nothing clear-cut about this.
sir.
And sometimes it will also depend on the soil profile. 1 minute. Oh, okay. Look at this. You can see it is, this is the water table. Can you see that? Can you see the ground surface here? Here is moving up, isn't it? So this could be a large area, isn't it? In which, based on what you say, we'll be expecting it to go this way, isn't it? So, but that is like shallow treatment of the case. You have to look at it in totality. If you deep down, this is like the real picture of the groundwater. So whether the topography is increasing or decreasing is immaterial. Did you get my point? So it can be this, it can be that, depending on the aquifers, on a lot of other things. Did you get my point? So that is the only point I want to make here. What do you want to say? Clear now? Okay. Okay. So normally coincides with the water table, and slope gives direction of groundwater movement in an unconfined aquifer. Now this is the unsaturated zone. These are the grains. You can see a small amount of water surrounding it, with air filling all the other void spaces. For the capillary fringe, you can see it that the voids are mostly filled with water, okay, with some small amount of voids filled with air, and then the saturated zone completely filled with water. Okay? Later on we are going to discuss about these voids, the properties having to do with the voids, the porosity and what have you, and what is it. And like this is the land surface. When you dig a well, let's say it stops here in the capillary fringe, you will find nothing inside, because the water is tightly held against gravity. It will not flow into your well. But if it goes here, then the water from the saturated zone can flow into your well, because it is readily available. I mean, it can flow under gravity. Okay? Still on the zones of porous media, you see we are still analyzing from the unsaturated to the capillary fringe and then to the water table or the saturated zone. Here we are talking about the vadose zone, the capillary zone. This is the water table. This is the variation of the moisture content against height, the vadose zone, okay? This is height, the variation of the moisture content. This is 100. At the water table, the moisture content also of the capillary fringe is usually 100%. Like I said, it is almost saturated. So for modeling the unsaturated zone, more often than not, the capillary fringe is considered to be saturated with water because it has moisture content of about 100%. That is why here you can see the water table, and this is the capillary fringe. Although probably later when discussing about the movement of contaminants, we will talk about this more. But what is called displacement pressure. Because when pulling water, let's say from the capillary fringe, you need some pressure called entry pressure or displacement pressure. Because the water is tightly held. And then it reduces. And then it becomes constant. It is never zero. Because this is the moisture content, this is the zero, okay? Because no matter what, some water will still be held by the porous media. So it will reduce and then it will remain constant, which is called the residual moisture content. Probably you might have done this in the engineering soil science. Residual moisture content, which is the minimum irreducible amount of moisture that the soil must always have. You cannot remove that, except of course by drying, by heating, but ordinarily you cannot just remove it. Okay, so but it has different patterns for wetting and drying. The reason for that is called because of hysteresis. Hysteresis happens because of what is called air entrapment, because in the unsaturated zone you have air being entrapped. If you keep on saturating the water, it will take that path up to saturation. But if you are extracting the water, it will not follow the same path because some air has been entrapped. Okay? And that difference is called hysteresis. Okay? We will talk probably more about that when we come to the discussion of the contaminant transport. And this is called moisture characteristic curve and is modeled using either Brooks-Corey model, developed in 1966, or Van Genuten model, developed in 1980. You might say we are taking so much time to discuss the unsaturated zone because water must pass through that. It is its pathway before it gets to the saturated zone. Because our main interest here is what the groundwater modeling, isn't it? So I would have as well just come and start with beneath the water table, what do we do? No. It doesn't just appear as, in the unsaturated zone. It passes through certain processes, certain stages, which you have to understand. Because understanding the hydraulics of the unsaturated zone will enable you also understand the modeling process, most especially for the contaminant transport again. Because the contaminant will also pass through the same thing before it reaches the water table. Okay? Now, let's define some few terms as it affects the unsaturated zone, or sometimes probably even the saturated zone. We have the volumetric moisture content. Just the moisture content in volume. This you must have done in soil mechanics, right? Soil mechanics. So back to soil mechanics. What is volumetric moisture content? Yes, yes. How is it expressed mathematically? The amount of water found in the soil, mathematically given by what?
V.
Just V.
Oh.
What?
Volume of moisture, all over total volume of saturated air.
What? Volume of? Moisture?
Or all over total volume of the saturated air.
All over total volume of?
The saturated soil.
BV over B.
Total volume of the saturated soil. So you are saying is volume of moisture, okay, volume of water over total volume of the including the soil matrix, the void spaces, isn't it? Because that is the total volume, right? Is that?
Volume of water over volume of solid
Volume of water all over volume of void times 100.
All over volume of void.
No, volume of water to the volume of soil.
To volume of what?
Soil.
Soil. Still we are divided. We will keep on being divided. You see, the moisture content, we want to find what is the amount you have void in the unsaturated zone. Of that void space, what amount of that void space is occupied by water? So in that case, the volume will not be the total volume. It will be the volume of voids. Because it's giving the percentage of the void occupied by water. Do you understand? The percentage of the void occupied by water. Okay? So this one should be VV. Okay? Then if you want it in percentage times 100%, okay? For unsaturated zone, what do you think will be the value? How will the value vary? Because it means the value will vary from 0 to 1, right? So for unsaturated zone, this moisture content will be, what will be, let's say the value? Below, up, Yes.
Saturated.
No, for the moisture content, what will be, it ranges from 0 to 1. So for unsaturated zone, what will be the range of the values?
That is for unsaturated zone now.
What?
This one for unsaturated zone.
What?
Very close to 0, 0 to 0.5.
0 to 0.979.
Can it be up to 1?
Relativity.
What about for confined aquifer? So for unconfined, it should be less than 1. Simple.
Yes.
And for confined? 1. Because all the voids are filled with water. Isn't it? Do you understand? Don't worry, we'll have also a short quiz now, which will be based on the understanding of these simple concepts. This is just fluid soil mechanics, isn't it? But like I said, now it's not just about memorizing, okay, this is the definition, this is the formula, and you can maybe solve problem. No. Now it's time to internalize all those definitions and the mathematical formulas which you know before, to internalize them. Now saturation. S. What is saturation? What is saturation?
Formally or the definition? Formally or the definition?
Both. What? What?
When the void space is filled with water.
And how do we relate it to the moisture content?
Is equal to 1.
How do we relate it to the moisture content? Intentionally left this here. This is the saturation. Someone mentioned it, but maybe he was not sure, and then when I said no, it's not like that, he didn't say no, but that is the one. This is the saturation, which varies from 0 to 1. Then the moisture content is VW over V total. Because in the void space, you have a lot of things. We just want to find out of the total volume, what amount of it is water. Okay? What amount of it is water. And then we move to the next one, which is porosity. Because in this case, for the saturation, it's telling you how saturated is it. Is it fully, that is the void space in particular. is the one that's specific about the void space. Is it fully saturated or partially or nothing? So it's specific about the void space in this case. Now the moisture content is now about the total volume. Okay? And then for the other one, the porosity. Now porosity. Very simple. Sure. Yes. Volume of voids over the total volume, right? Porosity and volume of voids over the total volume. So it's telling me how much amount of the total volume is empty space, isn't it? Or is void, isn't it? So it's giving the percentage of the void over the total volume, right? That is porosity. But then later, in the next lecture, we will talk about something called effective porosity. Because porosity, as it relates to groundwater, we are looking because water flows through the tiny spaces, the grains. You can see it flows, isn't it? Like this. Okay? It flows through the spaces, through the interstices. Okay? So that has great impact on groundwater. So we'll look at it because you'll agree with me that you can have a connected interstices and you have interstices that are not connected. The connected ones will contribute to groundwater flow. Right? The interstices that are connected, they will contribute to groundwater flow because they are connected. Those that are not connected, that are isolated, that have dead ends, will they contribute to groundwater flow? No. So that is why we will now define two types of porosities, or even three. We'll define effective porosity and just the general porosity. The general porosity is just measuring, for the unsaturated zone, it's referring just to the amount of voids present. But in the unsaturated zone, we are not just after the amount of voids, but those voids through which water can flow. There are voids in which you have water, but they cannot flow because it constitutes a dead end. They are not interconnected. So that's why we will go a step further to talk about what is called the effective porosity. That is the porosity which is now giving the amount of interconnected voids over the total volume. This is just the total amount of voids over the total volume. But the effective porosity will take care of the only interconnected voids, which is what we are after in the saturated zone. In the unsaturated zone, yes, this suffices. But in the saturated zone, no. We need to talk about the amount of the interconnected interstices. Is that clear? And then we will also talk about what is called primary porosity and secondary porosity. Okay? But that will be in the next lecture. Now, can you, let me quickly, this is our concept quiz, the first one. Derive the mathematical relationship for the following variables. Theta W, moisture content of water, moisture content of air, and porosity.
You have already written them.
What?
You have already written them.
They are already?
You have already written the mathematical formulas.
No, connecting them. One formula connecting these three. Did you get my point? Here I mean one single relationship connecting all these three parameters together. Is that clear? So, yeah, you can do it and I can go around. You can do it and I can go around. So no need probably to tear off your paper. Do it and I will check. But you must do it now. You have 4 minutes. So derive, this is the moisture content of water, this is the moisture content of air, and this is the porosity. Okay? When you are done, tell me so that I can come and check. Okay? And I hope I have my red pen to grade. I will have to get a red pen so that... no discussion. No discussion at all. No discussion. Done? Oh. This is judgment time.
That second one is theta A.
Yeah, moisture content of air. Yes. Who else is done? Who else is done? Yeah, all the three in one equation. All the three in one equation. Done? No. No. You cannot invite any other. The equation should be made up of only the... Then, judgment time. Okay. Done? But I see only one here. Where are the other variables? I see only this in the equation. I want to see only these three. Yes. Yes, yes, yes. You have 2 more minutes. Finish?
Yes.
All right. This is N?
This is air. This is water. This is air. So
This one. Check this. Yes. Done? Done? All right, all right. First attempt. And I hope you will get it on first attempt also. Why is... No, I didn't see N. I didn't see theta A and theta W. These are the only three things I want to see in the equation.
Okay, it should be in the form of theta.
Yes, yes, as they are. But I don't know how they are connected. Is it with lean? Is it with exponential? Yes, 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 yes. You have 1 more minute. 1 more minute. Just 1 more minute. You have to round up. Where's... Then how did you get this one?
This is the volume of white all over total volume. Then the total volume of of air is equals to the volume of weight is the velocity of air times total volume. So I substitute it directly. That's velocity.
Yes. But what about this VW? I don't see anything apart from these 3 parameters and VT. What about this one? Oh, your time is up. You now have to... Done? Is it times?
Yes.
Unfortunately, my time is up. Some of you got it right and some of you did not. And you know why I gave you this? It's not something that you must do even mathematically. It's just if you understood the definition of all these parameters clearly. So you can just even tell me. Some of you got it right, but some of you did not. I said derive because I know some of you will be thinking about some complex mathematical relationship, while it is not. It is like from first principle. Simple definition of these terms. What is moisture content? For water, the amount of water over the total volume, the amount of water within the porous media. For air, the amount of air within the porous media. Mathematically given by what? Volume of water if it's for water over the total volume. For air, volume of air over the total volume, isn't it? Now, for unsaturated zone, we have a void, isn't it? Which is occupied by what? Air and water, isn't it? The air and water, they fill up the void, isn't it? Then porosity is what? The volume of void over the total volume. Am I right? So porosity is the volume of void over the total volume. Porosity is the volume of void over what? The total volume. This volume of void, it has two components. Because the void, you have water and you have air, isn't it? Simple. So the void has two components. The volume of void is made up of what? Volume of air is made up of air and water over Vt, isn't it? And then when you separate Va over Vt, Vw over Vt, this is one, this is what? Theta A, right? And this is what? Theta W. So porosity is given by moisture content due to air plus the moisture content due to water. Very simple, short, and easy, isn't it? And as well as what? From your understanding of the simple definition of this, isn't it? We will have another quiz. So even if you don't get it right this time, don't be demoralized. We will have another one in the next class. Okay? So see you on Tuesday, right? At 9. A group Thursday, right? Oh, I didn't take attendance partly because I just came late and I forgot to bring. How many do I have today? 10. I have 15. Have you all attended my class yesterday? All of you?
No.
We have new faces. So who are the new faces? 2? Okay. So is there anybody who came yesterday and probably is absent today? Or probably the class, please take me the IDs of those that attended today, and then I will update it. Take the IDs, and a group has been created yesterday. I hope all of you are in that group. All of you? A WhatsApp group has been created yesterday, and I have uploaded I have sent the link to download the syllabus. That is the soft copy of that database password, and I also sent a link to download all the reference textbooks. Okay, but those that joined late, I think they cannot see the previous post. Okay. So please make sure you are part of the group, because we will be communicating through that, and any relevant material as it affects the course will be posted on the group. Okay. So make sure all of you are in the group. Okay. So see you on Thursday.